Hey everyone, and welcome to this rapid-fire board prep explainer. If you're an MLS student gearing up for the ASCP BOC, you are in exactly the right place. Today, we're kicking off a highly structured macro to micro bootcamp. We are moving at board review pace, which means it's going to be precise, it's going to be fast, and there is absolutely zero filler. We're going to build the fundamental blueprint of blood production from the ground up, laying the critical foundation you need for all of your future clinical interpretation. So grab your notes, get focused, and let's dive right in.
Okay, here's our roadmap for this session. We'll track from whole blood and smears down to the hematopoiesis timeline. Then we'll zoom in on stem cells, growth factors, maturation rules, and finish things off with the mature red blood cell. Section 1. Let's start at the absolute highest macro level, whole blood, and how we process it. Now, listen closely, because these baseline numbers are essential to everything we do. Total whole blood volume in an adult is 4 to 6 liters. Normal pH is tightly, and I mean tightly regulated, at 7.35 to 7.45. The composition is an exact split of 55% plasma and 45% formed elements. That's your red blood cells, white blood cells, and platelets. When you spin a tube down, notice how the buffy coat, which holds your white blood cells and platelets, sits exactly sandwiched right between the packed red blood cells at the very bottom and the plasma on top. Understanding this 55-45 split and the buffy coat's exact location is absolutely critical for specimen processing.
Moving on to smear prep. The gold standard technique uses 1 drop of EDTA blood to make a wedge smear. This is by far the most commonly used method, though cover slip or automated makers are definitely options too. For staining, we rely on pure Wright and Wright-Giemsa. These are Romanowski stains, and they're polychrome because they hold both eosin and methylene blue. Now, if you're using Giemsa, it adds methylene blue azure into the mix. Both of these are used to stain peripheral blood and bone marrow. We use methanol as the fixative to stick those cells to the slide, and right here is my massive instructor emphasis for a very high-yield board question. Your buffer must be exactly 0.05 molar sodium phosphate at a pH of 6.4. Lock that number into your memory right now. So, what happens when things go wrong? Well, let's break down this troubleshooting table step by step. If you have alkaline conditions, which can be caused by an alkaline buffer, an inadequate rinse, a prolonged stain, or even heparinized blood, your result will be gray red blood cells, dark white blood cells, and grayish eosinophils. Why does this happen? Because alkaline environments cause the cells to hyperabsorb that basic methylene blue dye. On the flip side, if you have acidic conditions, say from an acidic buffer, a short buffering time, or over-rinsing, the result is pale or reddish red blood cells and pale white blood cells. Acidic environments favor the eosinin dye instead. Finally, if your smear is just too thick, it dries too slowly, and the result is crenated red blood cells.
Section 2. We have our specimen. Now let's transition down a level to the systemic view, where blood is actually manufactured in the body over a lifetime.
This timeline is highly testable, so let's trace it rapidly through early development and then really focus in on the clinical takeaways for adults. From 2 weeks to 2 months gestation, hematopoiesis happens in the yolk sac, and the very first cell is the primitive erythroblast. From 3 to 6 months, the liver takes over as the primary site, aided by the spleen. By 7 months, the marrow becomes active in most bones. Then, at birth, the liver and spleen completely stop. Production moves strictly to the bones, and we see 90% red, active marrow. By age 4, fat cells start appearing in long bones and yellow or white marrow rises. Now slow down here and pay close attention to these adult years. By 18 to 20 years old, production is limited to the sternum, ribs, pelvis, vertebrae, and skull, leaving us with about 60% active marrow. By age 40, it's just the sternum, ribs, pelvis, and vertebrae. And after 55, only about 40% of marrow remains active. Notice the clear pattern here. As we age, blood production shrinks and retreats centrally to the axial skeleton.
But thankfully, our bodies have backup plans. Extramedullary hematopoiesis happens when the liver and spleen actually take over blood production again during times of severe systemic need. Think of a severe hemolytic anemia when the marrow just can't keep up the pace. Also, that inactive yellow marrow we talked about, it can actually revert back to active red marrow if required. Now let's talk about the myeloid to erythroid ratio, or M to E ratio. Normal is 4 to 1, but in severe infection, this can shoot up to 6 to 1 as the body frantically pumps out white blood cells. And here is a huge instructor emphasis point. Exactly 1 in 1,000 nucleated marrow cells is a stem cell. When you're looking at a normal marrow biopsy, you'll see a mix of fat cells, erythroid precursors, and granulocytic precursors all hanging out together.
Section 3. Let's zoom in even further to the exact stem cell hierarchy driving all of this production.
The whole show starts with the pluripotent stem cell. This is a cell that self-renews and yields not just blood stem cells, but also muscle, nerve, bone, and other tissues. From there, we get the hematopoietic stem cell, or HSC. Now, visually, the HSC looks exactly like a small lymphocyte. It absolutely cannot be identified morphologically under a microscope. So the mandatory board answer for identifying an HSC is that it's identified by phenotypic markers via flow cytometry, period. From the HSC, we get the MPP, or multipotent progenitor, which is committed to blood but still versatile. And that finally splits into the CMP for our myeloid lines and the CLP for our lymphoid lines.
All right, take a deep breath. This is the master map, and we are going to walk this chart branch by branch. So stick with me. Starting at the very top, we have the pluripotent stem cell. This divides into the myeloid stem cell, which is driven by IL-1, IL-6, and IL-3. And the lymphoid stem cell, driven by IL-1, IL-6, and IL-7. Let's track that myeloid lineage first. The myeloid stem cell becomes CFU-GEM. And really quick, notice how GM, CSF, and IL-3 label nearly every single arrow down this entire myeloid pathway. From CFU-GEM, we branch out. First up, the red cell line. BFUE becomes CFUE, which becomes the pro-erythroblast, ultimately yielding the mature erythrocyte, and this final stretch is heavily driven by EPO. Next, the platelet line. CFU-MEG becomes the megakaryoblast, then the megakaryocyte root eventually sheds thrombocytes. That entire process is driven by thrombopoietin. Now for the granulocyte and monocyte lines. CFU-GM splits. One side becomes CFU-G, moving to the myeloblast, then the neutrophilic myelocyte, and finally the polymorphonucleated neutrophil or PMN, driven by GSCF. The other side, CFU-GM, also becomes CFU-M, going to the monoblast, promonocyte, monocyte, and finally the tissue macrophage, completely driven by MCSF. Moving on, CFU-EO becomes the eosinophilic myelocyte, then the mature eosinophil, driven specifically by IL-5, and finally for the myeloid side, CFU-base becomes the basophilic myelocyte, then the basophil, which ultimately leads to the mast cell, driven by IL-3 and IL-4. Okay, let's jump back up to the top for the lymphoid lineage. The lymphoid stem cell yields the pre-B cell, which becomes a B lymphoblast, then, driven by antigen exposure, becomes a mature B cell and finally a plasma cell. Alternatively, that lymphoid stem cell can go to the thymus to become a prothymocyte, then a T lymphoblast, and again antigen-driven, becomes a mature T cell.
Section 4. That was a ton of info, but you have to know every branch. Now, let's isolate those ultra-microchemical signals and the cellular cycles driving these exact pathways.
This table right here is pure, high-yield memorization. Let's read every single row. EPO is produced mostly by the kidney, and it drives CFUE to the erythroblast and finally the RBC. Thrombopoietin drives the megakaryocyte to produce platelets. IL-3 and GM-CSF are the broad drivers for all myeloid lines. GCSF specifically drives neutrophils, and MCSF drives the monocyte and macrophage. IL-5 is specifically for our eosinophils, while IL-3 and IL-4 team up to drive basophils and mast cells. Finally, IL-7 drives the lymphoid stem cell.
As those cells divide, they follow exact cell cycle phases. You'll see these exact letters pop up constantly when we talk about leukemias in later sessions, so lock them in now. TG stands for one complete mitotic cycle. G0 is the resting or dormant phase. G1 is post-mitotic rest. The S phase is active DNA synthesis. G2 is pre-mitotic rest. M is the active mitosis period. And G and I indicates a non-dividing cell. Section 5. Now we apply everything we've just learned to track a single red blood cell line from its birth all the way to maturity in the marrow. Before we look at the specific cells, you must memorize these universal rules of maturation. These apply to all cell lines. As a cell ages, the cell itself gets smaller. The nucleus to cytoplasm, or N to C ratio, becomes lower. The cytoplasm becomes less basophilic, meaning it gets less blue. And that's entirely due to RNA loss. The nucleus itself becomes smaller. The chromatin condenses and nucleoli disappear. These are your golden rules. If you know these, you can accurately guess any cell's relative age on a smear.
This erythropoiesis process takes about 5 days in the marrow. Let's track the stages, reading every row and noticing the key changes. First, the ruberblast, or pronormoblast. It's 14 to 19 micrometers, has a 4:1 N to C ratio, has nucleoli, a deep blue cytoplasm, and one cell yields 14 to 16 mature RBCs. Next, the proruberocyte or basophilic normoblast. It shrinks to 12 to 17 micrometers. Notice the change. No nucleoli are present anymore, and the blue is much less intense. Next is the ruberocyte or polychromatophilic normoblast.
12 to 15 micrometers, 1:1 N to C ratio. Huge instructor emphasis here. This is the most plentiful stage in the marrow, and it is the last cell to divide. It has a gray hue because hemoglobin production has started. It's not normally seen in adult blood, but occasionally you'll find it in newborns. Next up, the metaruberocyte, or orthochromatic normoblast, also called an NRBC. 8 to 12 micrometers, 1:1 N to C ratio. It has highly condensed, pycnotic chromatin and a pale orangish cytoplasm. Another big emphasis, the nucleus is extruded right here. Next is the basophilic erythrocyte, or reticulocyte, 7 to 10 micrometers. It requires a supravital stain to actually visualize. It continues to make hemoglobin for 24 hours after leaving the marrow and matures in 1 to 2 days in the peripheral blood. Finally, the erythrocyte, or discocyte, 7 to 8 micrometers, biconcave, flexible, and deformable. No nucleus and zero hemoglobin production occurs here.
Section 6. Let's conclude our structural review by looking specifically at that final, mature product that circulates in the blood.
The mature RBC has primary jobs. It transports oxygen and removes carbon dioxide. Simple enough. It has a 120-day lifespan, deriving all its energy straight from glycolysis. The cell volume is roughly 90 femtoliters, and that size is maintained by active sodium/potassium pumps. Structurally, its membrane is 50 to 60% lipid, that's phospholipids, cholesterol, and glycolipids, and 40 to 50% protein, which is mostly spectrin and glycophorin. Under a microscope, you'll see a central pallor of 1 to 3 micrometers. This pallor gets larger in anemia and is decreased or totally absent in spherocytosis. Finally, note that 100% of mature RBCs circulate. They are never stored in the spleen the way platelets are.
Before we wrap up today, I want to give you the ultimate board-saving cheat codes. These mnemonics will absolutely save you when you're under pressure. For the red cell maturation sequence, just remember, really pretty red meat rarely rots. That stands for rubroblast, proruberocyte, ruberocyte, metaruberocyte, red cell, and RBC. How do you tell the first two apart? The rubroblast has nucleoli, the proruberocyte does not. What happens at the meta stage? Meta means nucleus missing, because it gets extruded. Don't forget, the ruberocyte is the last cell to divide. And for staining troubleshoot, alkaline equals dark or gray, acid equals pale or red.
Well, you've made it through the boot camp. You now have the fundamental blueprint of blood production completely locked in. But here's the critical question I want you to carry forward. How will all these perfect baseline numbers and neat maturation rules shatter and shift when we introduce a leukemic blast or a massive hemolytic crisis? We are going to explore exactly that in our upcoming explainer sessions. Keep reviewing these foundations, and I'll see you there.